Okay, thank you for coming along this afternoon. It's a very late hour, but I'll try to keep it in longer than I have to. So, MLA is a revolutionary touring system that uses intelligent software to control the individual DSP and onboard amplifiers of up to 144 acoustic cells per array. MLA's combination of cellular drive and automated optimization software removes the guesswork and trial and error, delivering the engineer's mix throughout the venue with an accuracy and consistency not achievable with traditional line arrays. MLA may look like a line array and fly like a line array, but there the similarities end. So what issues does MLA address? The first one is consistency. So we have a poor person there who's gone to the show and they're just sending their friend a text message saying, can't hear the words off to the bar. So we want to get rid of that kind of performance. The other thing that we want to address is the fact that we believe there are inadequate tuning tools available to the system technician. Typically you've got a few channels of DSP, then you're into doing things like turning amplifier channels down in order to try and tune your system. They're not 21st century solutions, we think. The other thing as well is setup time. We're never going to get any more time to set up a show, so that means that all of the goals of the MLA system need to be achieved either within the same amount of setup time or with an even less time than we're given at the moment. And another very thorny issue is which preset to use with your touring system. Do you use manufacturer's presets? Does one preset work better than another? Do you roll your own? We want to again get away from the idea of the success of the quality of the sound reproduction being very dependent on someone choosing the right preset for the right situation in hand. So the design background. Early touring line arrays were usually driven by the same audio signal throughout, i.e. one-zone systems like you see on the left. And today, touring line arrays tend to be driven in 3 or 4 step zones to which different EQ can be applied in order to linearize, regularize the output of the system throughout the venue. But simple zoning like this is too coarse to reproduce the engineer's desired balance and level throughout a large venue. In contrast, a 24-box MLA array has 144 individual cells, each automatically EQ and level optimized for the audience profile. So looking at some measured responses here, these were actually taken in Earls Court 1 about 7 months ago. And we can see in the bottom graph there a frequency responses taken of the array from right up close to it to about 80 meters away, so the back of the floor in Earls Court 1. And they look pretty consistent to me. And you might ask, well, how did we achieve that? And the simple answer is these results were achieved right from switch on by putting the geometry of the venue into our optimization software and then letting the software figure out how to drive each of the DSP channels within each of the cells of the array in order to generate these amazingly consistent results. And within the optimization software we can set targets like frequency response smoothness, SPL variation from front to back, so you can set how much louder it is at the front and how much quieter it is at the back compared to the sort of nominal 0 dB at mixed position. And you can also do things like set how important leakage is to you. So if you've got a very hostile acoustic environment and you want to make sure that outside of your covered sound field you want to minimize as best you can the leakage, then you can set that as an optimization target as well. And those 3 factors, frequency response, SPL variation from front to back and leakage, are all balanced together into the objective function of the optimizer. So just taking a look at what's going on in the MLA system, how does it actually achieve these results? So here's an 8-box array, and in each MLA we've got 3 high-frequency channels, 2 mid channels and 1 LF channel. So in an 8-box MLA array we've got 24 HF channels, 16 mid, 8 LF equals 48 independent channels. So there's no way that a human can actually optimize the DSP coefficients and transfer functions of those channels by hand. There's just not enough time to do it. So we need to get the computer to do it for us. And in order to do that, we've had to generate probably the most accurate model of array behavior in the industry to date. So we can predict from measured to predicted plus or minus 1 dB variation. We did an AS paper about 2 years ago which actually proved that we can achieve that. So within each MLA we've got these 6 channels of DSP, and in order to generate these amazingly consistent frequency responses and SPL variations from the front to the back of the system, we're using FIR filtering. And that's because what we need to do is manipulate the magnitude and the phase of the signal to each individual cell independently. So just looking at the, at the graphs on the left, on the y-axis we've got the top of the array at the top, and coming down the array we've got each sort of cell right from the top down to the bottom is each of the points on the y-axis. On the x-axis we've got frequency, and we're using colour to denote magnitude. So you can see, for example, the dark blue bits just denote where the crossover points are between the mid and the HF sections. So we can see that the magnitude response varies a little bit from cell to cell, but far more interesting are the plots on the right, where we're looking at how the phase varies from frequency to frequency and cell to cell. You can see there's a huge amount of variation there. From dark red to dark blue, we're talking about variations of plus or minus 180 degrees. And this is why we see the MLA as being a post-line array product, because the goal of line array designers to date, including our products that are on the market at the moment, has been to generate isophasic waves at the loudspeaker grills. Now we're moving beyond that goal. We're moving to optimal vector summation in the audience plane, actually where people's ears are. So that's where we're concentrating on producing the optimal summation of the wavefronts from the system. So looking at how MLA copes with some of the real-world problems that you might find in a touring environment. Here we've got a very simplified image of the array covering a certain part of the venue. And for example, the tour manager or the promoter has said, guys, you only need to cover this part because that's all the seats that we've sold tickets for. So don't bother covering the rest. And then what happens when the audience come in, but they go and sit where you've not been covering. So with a traditional line array system, you're out of time there because you can't pull the system down, change your spline angles and re-rig it. You're stuck. You've got to try and persuade the audience to come and sit where you're covering. Whereas with MLA, all you need to do is put the new coverage pattern within the optimization software. It will recalculate all the DSP coefficients, and without changing any splay angles, without changing any rigging heights, you can, within a certain angle, get the MLA to broadband adjust its coverage. You can also adjust coverage close to the stage as well as far away from it. And perhaps even more impressively, if you've got a very difficult acoustic surface in a venue, like a balcony, you can actually notch out the coverage to miss the balcony front. Typically we can broadband turn level down by about 12 dB or 15 dB, which is a really, really useful reduction in reflection from these difficult surfaces. And again, it's all just done with DSP. There's no physical alteration of the array necessary to do that. So the acoustic design of the MLA, it's an all-hole loaded design to maximize efficiency. The mids and the high frequency drivers are on constant directivity horns for exceptionally smooth off-axis response. This gives the product a very, very wide and stable stereo image. And the peak output of each MLA is in excess of 140 dB at 1 meter. So it's an incredibly powerful product. As well as having the DSP and amplifiers on board, MLA has an audio network called UNet, which is a proprietary technology of Loud Technologies. And this is what's used to actually enter in all of the DSP coefficients within the system automatically via this network. Here you see a tablet PC running our network management software that we call ViewNet, and from within that application you can see all of the MLA nodes in the network, and you can control and monitor them all individually. So, looking at the economics of efficiency, we asked ourselves, can we design a sound system to be more energy efficient? And first of all, because MLA's inherent acoustic efficiency is extremely high, we're winning in that respect, but we're using other techniques as well, like power factor correction in the amplifier's power supply, and that means it presents a non-reactive load to the main system, so it's just drawing watts rather than VARs. And typically we found that MLA draws 60% of the mains current when compared with our existing line array systems whilst delivering the same SPL. So there's a definite saving there in terms of the electrical power required by the system, which is extremely tangible. And all of this is in a very compact package. I think you can see the product over there. It's a remarkably compact enclosure given the output capability and given that it's got 6 channels of amplification built into it too. So that means that you can get more SPL into a smaller truck pack. This truck here is a 7.5 tonner that we brought the whole system to Earls Court 1, and that was 24 boxes. And you can see from the photo that the truck's not even half full. We haven't even had to stack the boxes. So every time the system's moved, then it's saving fuel and therefore it's saving money.